Enantiomeric excess is another important concept related to chiral molecules. Before I can actually define what enantiomeric excess is, I need to define a couple of other terms for you. One of them is called a racemic mixture. A racemic mixture is defined to be a one-to-one mixture of enantiomers, exactly a one-to-one mixture. And the way that you typically get racemic mixtures is if you're doing a chemical reaction that produces a chiral compound from achiral starting materials. Okay, so one important example is if you take an alkene and turn it into an alcohol or an epoxide. If the alkene is achiral, the alcohol and the epoxide will sometimes be chiral, but you will get a racemic mixture, a one-to-one mixture of the two enantiomers. Anytime you have a mixture that is not, where the ratio of enantiomers is not exactly one-to-one, we call that a non-racemic mixture. And non-racemic mixtures usually arise under one of the following two circumstances. The first one is if you're charged with the task of separating the enantiomers in a racemic mixture. Okay, that is an experiment that is commonly done in organic chemistry lab, in which case you use some other chiral compound called a resolving agent to react specifically with one enantiomer and not the other one, and then therefore, because one enantiomer reacts, the other does not react, you have achieved partial separation. However, even with the best chiral resolving agents, that separation is usually not perfect, and after one round of separation, you end up with a non-racemic mixture, albeit one that is enriched in one enantiomer. The other case is if you do try to synthesize an enantiomerically pure chiral compound, which of course is what the Food and Drug Administration now wants you to do if you are preparing a chiral drug, you will frequently use a molecule called a chiral catalyst. Okay, you will use a chiral molecule to catalyze a reaction of an achiral starting material to hopefully give a single enantiomer of a chiral product. However, with many chiral catalysts, the reaction does not proceed with perfect enantioselectivity. There is still sometimes a small amount of the undesired enantiomer that is produced. And sometimes, if it's not a great catalyst, there's actually a large amount of the undesired enantiomer that is produced. Okay, so in both of these cases, it is necessary to report a number indicating what level of enantiomeric purity you have. And the standard means of reporting enantiomeric purity is this term called the enantiomeric excess, also known as the EE, lowercase e's, which is defined as follows. Okay, if you have a mixture of enantiomers, the percent EE is the difference over the sum times 100, or moles of major minus moles of minor over moles of major plus moles of minor times 100. Okay, let's put this definition into practice. So what you would need to do is figure out what the enantiomeric excess is of a mixture containing 80% of the R enantiomer of a compound and 20% of the S enantiomer. Okay, so how do we do this? Well, you go back to the definition. What goes on top is 80 minus 20. What goes on the bottom is 80 plus 20. Conveniently, I set up this problem so that what's on the bottom adds up to 100. So that's 60 over 100 times 100 in order to get this as a percentage. So an 80 to 20 mixture has a 60% EE. Okay, this definition may seem a little bit strange to you, but the reason why we use it is that the EE, as defined this way, is directly proportional to optical rotation. In other words, a mixture with 50% EE will have exactly half of the optical rotation of a pure enantiomer, and a mixture with 25% EE will have 1/4 of the rotation of the enantiomerically pure compound, or half the rotation of the 50% EE compound. So that's why we use this definition of EE instead of simply reporting the ratio of the enantiomers. Okay, so what's a typical problem that we might have to solve using this concept? You will be given that enantiomerically pure R2-bromobutane has an optical rotation of -23 degrees. And somebody gives you a sample, you go into the lab, and you measure an optical rotation of -14 degrees. What you have to come back and report to your supervisor is what is the EE and which enantiomer, R or S, is there more of in your sample. Okay, so let's solve this problem. First, to get the EE, you simply take 14. You ignore the sign for now. You take 14, put it over 23, punch those numbers into your calculator, multiply by 100, and you will get that this particular sample has an EE of 61%. Now, to answer part B, you have to look at the sign. The sign of the observed rotation is negative, and you're given that for this particular compound, the R enantiomer has a negative rotation. So what that means is if you observe a negative rotation, there is more of the R enantiomer than there is of the S enantiomer. Had you observed a positive rotation, then there would be more of the S enantiomer. Okay, also note that a racemic mixture is defined as having 0% EE and exhibits no optical rotation. Okay, so when you have a racemic mixture, you still have a chiral molecule. It's just all of your R cancels out with all of your S, and this is a case in which a solution of chiral molecules will exhibit no optical activity.